Have you ever wondered why tensors are so vital to grasp when studying general relativity? What makes tensors so essential in understanding the curvature of spacetime and the nature of gravity? Why tensors are used widely in every sphere of physics, mathematics, engineering, and data analysis? Was Einstein aware about tensors and its importance? In this video, I am going to answer all these questions and will take you deep down in understanding the tensors and its role in modern physics. We will also going to look into the remarkable history of how Einstein came to discover about tensors and thereby formulating his theory of relativity. This video will cover every single details about tensors and its importance and how it is used in general theory of relativity. Before I go ahead, I would like to inform the viewers to look into my thank you screen at the end of this video as it contains something new which you are going to like. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the beginner's guide in tensors in having a better understanding of the space-time and general relativity. So first let us quickly look what are the topics that we are covering today. First we would talk about what are tensors, how tensors came into mathematics, tensors and crystal structures, why they are used in studying, what is called the rank of a tensor. We are also going to understand what is the nature of tensors, why they are unique. Can we use tensors to write Newtonian or classical equations of mechanics? What is the role of tensors in general relativity and how Einstein came to know and discovered tensors about framing the equations of general relativity? What are the tensors that are used in general relativity, Ricci-curvature, Ricci-scalar, and further on. So having laid above these topics, and we have already talked about what we are going to discuss, first we will understand what are tensors. Now as we talk about tensors or any mathematical or physical concept, as we know it all comes from the Latin words. So here the first word, Latin word tender, actually it means stretch. So obviously in anatomy tensors are called as a muscle that tightens or stretches a part of the body. Now if I take these two definitions, the Latin definition and the anatomy, then we can understand that it has got to do something related to stretching or pulling or squeezing, and that is exactly the meaning of tensors, as we will discover in the further part of our video how tensors originating from Latin word actually talks about the stretching of certain components. Now if I take a sphere over here and if I stretch it, because it talks about stretching of the muscles, if I stretch it, it becomes an oblate spheroid. What I do is that I will try to understand the information on the sphere which is marked in the red over here, and if I put it over in the oblate spheroid after stretching, the question is that how will we come to know about the stretched information? So original information from the sphere getting stretched into oblate spheroid, how will we come to know about the stretched information? And that is exactly what tensors does. It stores some amount of stretching information. What we will later encounter in this part of the video. Here is a mathematical definition. It can be called as a set of components, functions in the coordinates of any point which can be transformed linearly between coordinate systems. Well, I understand that it is a very technical definition, but don't worry, we will make it easy and look forward. But what we have understood right now from the origin of the words, it stores some amount of stretching information when the original component is being stretched. So the tensors, we can talk about different type of definitions. It says that is just an n-dimensional array with indices. Tensors are simply mathematical object that describe physical properties. Tensors are vectors that do not have a single direction but rather point in all direction. Some definition says that it is a multilinear relationship between sets of algebraic objects related to a vector space. Now why I am saying all those definitions? Because these are all the same. In future when you come across this type of a definition, you are not taken aback or you are not feeling confused. However, the best definition comes here. We can call it as our tensors are containers. That means it is a kind of a object which contains what? It describes the data or physical entities in n dimensions. Most important, when we will be seeing that as we increase the dimensions, the orthodox or the general properties of mathematics are unable to describe. So it describes n dimension, and it is a physical quantities which not only have a magnitude but also it has multiple directions. So this is the basic definition. It contains dimensions and it does not have magnitude but many other things which have got multiple direction. So what does actually this tensor looks like? Approximately it looks like this. So we can tell that these are vectors which do not have a single direction but they are actually pointing in different direction. We can also call that they have properties of both vectors and scalar like areas and stress. Tensor, I would say it is not a scalar, but it obeys some kind of a coordinate transformation law we will later discover, and we can tell that tensors are geometrical objects that describe the linear relationships between geometric, numerical and tensile vectors. What do I mean by tensile vectors? I will come later. So this is all in all a kind of a very basic layman understanding of what is a tensor. It doesn't have a single direction. It has multiple direction. It obeys certain kind of a transformation rule, and mathematically they are geometrical, numerical and has got a linear relationships. We will discover more and things will become easier, but now it is the time that now that we have understood the definition of tensor, the question is that who discovered tensor, or how tensors basically came into mathematics, coming up into this part of our video. So if we go back to history quickly, we see that it was Augustin Louis Cauchy in 1822 who used tensors, calling as Cauchy stress tensor. William Rowan Hamilton, we will soon see that Hamilton actually coined the term tensor, used as tensor of the quaternion in his famous work. Then it was Bernhard Riemann 1861 who used Riemann curvature tensor, and Joshua Willard Gibbs in 1884 used something called dyadics or polyadics, basically in order to study something like crystal structures, but these are actually tensors, but during that time it was used as dyadics and polyadics. With Joshua Willard Gibbs, further we come to know this wonderful person, Dr. Waldemar Voigt, 1898, and he used and discovered tensors while studying stress and strain on crystals. And then it was Gregorio Riccicurvatureexplained in the late 1800, whose riccicurvature tensor, as we will see, is extensively used by Albert Einstein, Ricci tensor, and finally Tullio Levi-Civita, the Italian mathematician, used tensor to come to know something which is called a tensor calculus. Now this is how actually the tensors are, I would say, a very brief history, although there are a lot many to cover, but this is a kind of a very brief history of how tensors actually came into mathematics, and this is how it is actually invented, or you can say rediscovered using some physical phenomena or studying some physical phenomena. Now the question is that now that we understood the basic tensor, also we have understood how tensors came into being. Now the question is that how can we know that what were the original paper through which tensors came to being? So you see Dr. Waldemar Voigt in this famous book, which is in German, means the fundamental properties of crystals. You will see that here I have underlined, it is a German book, so I've just underlined those lines where he used the word tensor. So you can see 1, 2, 3, 4 tensoren and tensors. So this is, we can say, that one of the historical references which uses tensors basically when he was studying the fundamental properties of crystals. Further we see William Rowan Hamilton also using tensors, and this is quite easy because it is English, in his famous book published around 1884 to 1850 when he was studying on quaternions, and you can see I have underlined tensor, 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 tensor. So these are the references which actually shows how tensors actually came into mathematics, who were the people who studied tensors. But the question is that you will see that when you study deep into the history of tensors, tensors are primarily in the earlier phases were used to calculate the I would say they calculate the problems or the lattices of crystals. So the question is that what is so typical in crystals and what is so typical in tensors that we need to study the crystal structure. Coming into this part of our video, why tensors are used to study crystal structures. I will give a very simple example. So this is how more or less the tensors look like, right? But when we study the tensors further, I mean to say, when we are expanding the structure of tensors, it looks like this and it looks like this. So immediately you can recall from the earlier definition that the structure of crystals that we see right on the screen on the right hand side, these contains many lines, many directions, many planes. It is quite a complicated structure. So if I expand the crystal into a further kind of a study, then it looks like this, right? Simple and phase terraced, rhomboedal, phase terraced, and further if we expand this, it will also become this. So you understand that studying the structure of crystals becomes so very complicated because it is a body center, it is a tetragonal, it is a hexagonal, it is triclinic. So all these structures which you can see right now on the screen are actually contains different magnitudes. It cannot be defined by vectors. Why? Because it doesn't not only have a magnitude and direction, but it also have different planes, different sides, and that is why tensors are used. Let us quickly look into the next part of our video. So many faces and many directions actually forces us to use tensors. Now let us see a very simple example. If I take a kind of a glass, and if I heat it, then what I can tell you that it will expand by the same amount in each direction. This is a property. But if I take a kind of a crystal and if I start heating it, you will see the expansion will differ depending on whether one is measuring parallel to the A or B or X and Y axis. So that is why the elasticity and thermal expansivity cannot be expressed as scalars. So this is the reason that tensors are used to study crystals, because tensors are tools which deals with more complex situation, and because single crystal properties are very important in order to understand the bulk behavior, because once we understand one crystal, we can generalize to understand the bulk behavior of rocks. We wind up dealing with tensors fairly often in what is called mineral physics. And obviously crystal structure is one of the prime factors of understanding mineral physics. So what we understand from here is that because of the complex structures, because of the different planes, faces, etc., normal vectors or normal mathematics cannot study the crystal structures, and here we use something which is called tensor. So if you want to measure the forces imposed on a single crystal in deformation apparatus, we are really interested to understand the stressing acting on various crystallographic planes. Now this is what is called a crystallographic planes, right? So in terms of crystallographic coordinates, so tensor mathematics actually allows us to calculate the stresses acting on different crystallographic planes and transforming the stress tensor from one coordinate system to another. Here on the right hand side direction, I've given a very trivial example of how stress and strain are acting on different parts of the cube, and what we get is a kind of a matrices which is further expanded into tensor. So note here the last line is very important, which we are going to explore further. That is how we can transform these crystal which we are studying in crystallographic planes from one coordinate system to another. That means if we come across another feature of tensor, not only planes or complex structures, if we want to transform the crystal from the crystallographic planes by transforming the stress tensor which is prevalent in one coordinate system, tensors also come to use. So in this part of the video we have clearly understood that why tensors, what are the definition, a little bit about history, and why tensors are used in understanding the crystal structures. Now the question is that there is something which is called very important, called the rank of a tensor. We will not go too much into the difficult mathematics, but visually we will understand what is the rank of a tensor. So in general, a scalar is a physical quantity that is represented by a dimensional number. Now a vector is basically also a tool which keeps a track of magnitude, direction, etc. Now if I take this vector has got three components which can be easily written by this: v1x, v1, v2x2, v3x3, which can be summarized and written in a matrix form. But the question is here, what happens when we need to keep track of these three pieces of information for a given physical quantity? So for that, what we need is a tensor, and that is why we need what is called a rank of a tensor. So if you see this x1, x2, x3, and if I draw it on a simple stress, I will get something like this. Now what actually is this omega ij, omega 1, 1, 1, 2? Let me explain one by one. So the first component, actually this 1, keeps track of the plane the component acts on. That means, as we have seen crystals or other cubes, there are different planes. So 1, 1 or 1 to the first one, which is a kind of an index, which we will soon see, it keeps the track. That means the pressure, stress or strain, whatever is acting on which plane, right? Second, what we do is that it keeps track of the direction. So on which direction, x axis, y axis, z axis, or whatever direction it tells in. So here we define, this is what we call the rank of a tensor. So rank of a tensor is defined as the number of dimension of the tensor. The shape of the tensor represents the size of each dimension. So the tensor, actually we will see later that when it changes the shape from 1, 2 and 3, it actually represents the dimension. So now we got another striking feature of what is a tensor or what it is typicality. That means it actually represents not only the plane in which it is acting, but also in dimensions, because crystals actually comes in 2, 3, and we will see relativity comes in more dimensions. So here a number scalar, it is called a rank 0 tensor. This one is called a rank 1 tensor. This is called actually rank 2 tensor. And then we got further complexities. This is a kind of a cube which further can define rank 3 tensor, etc. And then we get something which is called rank 4, very difficult to show, then rank 5, rank 6 and so on. Although we don't deal with rank 5 or 6 in general with general theory of relativity, but this is a kind of a understanding that tensors, ranks, and what do we do. So these ranks of tensors actually helps us to understand the crystal structures, because the complex crystal structures, when we move from one coordinate to another, the shear stress, the strain acting on those crystals can be easily defined using tensors. Now the question comes that we understood the rank of a tensor, we understood why tensors are important in terms of calculating crystal structure. We also understood the definition and something which is more than magnitude and direction, that is what is called a tensors, what the tensor measure. The question is that why tensors are very unique. That is the basic question. What makes it very unique? And that is why it is used in relativity, coming up into the next part of the video. So first thing what I would say is that if you look into this kind of a illustration, you will see that these tensors are basically a kind of a generalization. Although again it's not a very good, I would say a very good understanding of tensors, but yes, it actually generalizes scalars, vectors and matrices. So tensors actually extend the concept of any number of dimensions, and that is why it allows the representation of more complex data. So why tensors are unique? One, it generalizes scalars and vectors. Two, it expands the concept of dimensions into further, which helps us to store complex data. So here you see it is rank 0 tensor. Here it is called rank 2 tensor. It can be dimension 5. This is 5 by 3 matrix, rank of dimension 2, and this is what rank 3 tensor, but it has got dimensions 4, 4 and 2, which is very difficult to show. And index or rank, you see this is 0, 2, 1. This is 0, 0, this is 2, and this is rank 0. The left hand side, rank 0, then we come to 1, 2, index 2, then we come to rank index 0, and there's 0, 2, 1. So this is a flat scale or a flat Euclidean space. Now you see, when I transferred this into curved space time, this is what it does. So the curvature of space-time is described by what is called a metric tensor. We will see what is a metric tensor, which is basically a rank 2 tensor, and you have already understood what is rank 2. So the metric tensor, actually when we move from flat space to curved space, it will actually show how we can measure the distance, the angles in space-time. It also tells how objects move in space-time, and typically these are called geodesics, and we will understand what is geodesics in this part of the video. So this is actually why tensors are very unique. We will look into further details. If I've got a flat space-time where I'm measuring a kind of a vector A, and if I divide this vector into AY and AX, these are the components of vector, we can understand very well in flat space-time. So these blue dotted lines actually shows the components of the vectors. Now if I get a kind of a curved space-time where I'm plotting or immersing the same flat space-time, then if you're measuring the same vector A, you will see this A prime X becomes longer and A prime Y also becomes longer, and the basis of the vector actually changes. But the vector remains the same. So here A prime X and A prime Y is longer and A is invariant. So this is also another feature of tensor, that when we are moving from flat to curved space, the basis of the vectors are changing, but the vector remains invariant. Let us look into this part of our video. So you see, this is a kind of a curved space, this is a flat space time, and here you can see that this AX is this one, AY is this one, and this is the AX and AY. But when we are moving and rotating that frame of reference, the A prime X becomes bigger and the A prime Y also becomes a little bit shorter. So from the static frame of reference, when we are moving into rotating frame of reference, we can see that the components of the vectors are changing. Some of them is becoming bigger and shorter. And on the right hand side, which is bothering you right the moment I started, this G00, G01, G02, this is what is called the metric tensor, and this metric tensor actually measures the causal structure of space-time. That means how much the components are bending, how much it is curving, all those stuffs. So if I get a person who is throwing a ball in one frame of reference, and that same person is throwing a ball in a rotated axis, both of them has got certain events which is happening. So what the postulates of general relativity tells, that events will be measured in the same way in all frames of reference. So again, if I take this person who is throwing a ball, and if I take the same person throwing the ball in an extended axis, it will always be the same. So events will be measured in the same way in all frames of reference, irrespective whether it is twisted, rotated, or even extended. I can take a sphere, and this is the red line which you can see. If I stretch it, it becomes an oblate spheroid, and the information which I just showed you right at the beginning, from this structure, when it expands and gets stretched, the red line also gets stretched. However, the information stored and the measurement will be the same. This is the famous quotation of Einstein: the general laws of nature must be expressed by identical equations relative to all other systems, whichever way we are moving. So it is moving in whichever way, it is getting stretched, squeezed, etc. But the laws of nature must be expressed in identical equation. This is another very important feature of why tensors are unique. Another important feature which comes from here, I would take a step back, is that we know that the space-time, which was basically a three-dimensional space-time in Newtonian mechanics, got stretched into a four-dimensional space-time. So here is the time, this is the time t, and x, y, z are the spatial dimensions. And from special relativity, and if we move into general relativity, we find that space and time is now taken up in a lump which is called a space-time. So in this four-dimension space-time, even if that person is throwing this one and this is being thrown in this one, the rotated axis, we will again be that the universal laws of physics should not depend on any particular coordinate system. So events will be measured in the same on all frames of reference, whether it is time, space-time, or we take a lump and unite it into space-time. Universal laws of physics should not depend on any particular coordinate system. And that is the role, another important role of tensor, specifically called metric tensor. So the metric tensor describes how distances are measured in a given space-time, and it is used to turn specific coordinates that we use. So I hope by this time you are already getting a hint that why tensors are unique and why it is used in general theory of relativity. Now, Another question which comes is that if tensors are so important, why tensors are not used in classical physics or Newtonian physics? Coming up in this part of the video. The big question is that all these equations of motion, the first derivative, the second derivative, here I've got the Suvat equations, angular momentum, etc. All of them are basically taking in what is called a flat space-time. Now, when things are taking in flat space-time, what does it mean? It actually means this, that Newtonian mechanics operates within a three-dimensional Euclidean space, and it doesn't consider the curvature of space-time. And most importantly, things can be used by Cartesian coordinates or simple by these vectors. So if we can use these vectors in order to determine or calculate the motion, angular momentum, work done, Suvat equations, differential equations, then obviously we don't need tensors. Obviously we don't need tensors because it is all occurring in flat space-time. Yes, we can define Newtonian laws in terms of vectors, but that is not why we need tensors. So this is the reason that because of the flat space-time, we do not need tensors. But the question arises that can we write any one of the Newton's equation using tensors? The answer is yes. Now I will show you this equation. I have just taken this one, the force. This Fi is actually, I have taken multiple I would say particles, right? So Fi denotes the force acting on the ith particle, m is the mass of the particle, xi means position of the ith particle, it can be at x, 1, 2, 3, 4, I have taken it I, and this entire d square x pi by dt square, which is a second order derivative, it is actually the acceleration of the particle. I have written it just in terms of I, that is Einstein summation convention. I can write it as this, right? And Fi is again the force acting on the ith particle, rest of the things remains the same. And here is something new, which is Tij, and this is called the stress energy momentum tensor. What it tells, we will come into the later part of the video, but everything related to stress, energy, momentum, angular momentum is being stored up in one small container, which is called the stress tensor. So yes, we can write Newton's equations using tensors, but this one, which is not at all necessary. Why will we unnecessarily delve into complexities? So we avoid using tensors in Newtonian equations, but this is something to tell you that we can write it in in Newtonian mechanics. So you see, vectors are good enough to describe I would say Newtonian mechanics, whereas in curved space-time, you see this is curving, vectors cannot describe the physics. So when I transfer from a flat space to another flat space, it will be another flat space only, and the laws of nature obviously will be invariant. I'm talking of Newtonian physics. But when from I would say from the flat space-time using general relativity, when I take this kind of a curvy space-time, then we need tensors, because the laws of nature won't be invariant. But the postulate general relativity tells that the laws of nature should be invariant, and that is why we use tensors. So this is this part of the video gives you clear clarity of why we cannot use, I won't say cannot use, but why Newtonian physics or classical mechanics do not use tensors, because it is not necessary. There is no curvature, there is no covariant derivative and other complexities. It is flat to flat. But yes, I have shown you that we can use tensors in order to write experimental basis Newton's law. Now the question is that after using these laws, the question is that what is the role of tensors in general relativity, or I would say what actually is the function of tensors in general relativity, coming up into this part of our video. So the first thing is to measure the curvature. Now here is a flat surface and this is a red straight line which goes, and when I get a kind of a curved surface, you see that line moves and takes a curvature. What does it mean mathematically is that I cannot use the same Euclidean or Pythagoras' theorem, hypotenuse square, this one, and I cannot use x2 minus x1, which leads to this and this cannot be used, because it won't work in flat surface. So I need something which is called a metric tensor, and this metric tensor actually defines computing length of curves manifold, infinitesimal distances on manifold, and it will come something which is called tangent vectors. Yesterday only I made a video on how tangent vectors are important in differential geometry. So this is one. So in order to measure the curvature, the entire mathematics needs to be changed. The good old Euclidean and Pythagorean theorem cannot be used in the curve space-time. Second thing is that it is invariant measurement under coordinate transformation. What do I mean? I will use the same example, the person throwing the ball, and I will use the same when it is on a rotated frame of reference. So events will be measured in the same frame of reference using metric tensor. This is how the metric tensor looks like. It describes how distances are measured in space-time. So here again the same example, it is being rotated over here. I will just skip this part because you already know events will be measured in the same in all frames of reference. So whether it's a rotated axis or it is a extended axis, it will always be the same, and whatever be the frames of reference. So the sphere which has got this kind of a curvature gets extended into an oblate spheroid. So this will also be the same as per the postulate of Einstein, which tells that equations relative to all systems whichever they are moving. The next thing which comes very unique is the measurement of dimensions. This is unique and it was never present in Newtonian mechanics. You see, the 3 dimensions which you used to do in Cartesian coordinate or classical mechanics now has got extended into a 4-dimensional space-time. This is what is called 4 dimensions, and for that we need a tensor, because from 3 dimension, again as we will go into 4 or maybe 5 or 6 dimension, we have noted that tensors do play a vital role in measuring the dimensions. So here you see bottom one dimension tensor rank. We can say the rank actually denotes the dimension: 2 dimension, 3 dimension, 4, 5 and 6. And now with string theory coming in, this is a kind of a pictorial illustration. You will see that people are saying that string theory, Kaluza-Klein, etc. They're telling that their entire dimension is curled up into a Calabi-Yau manifold, and which can be 6 dimensions. Somebody says 11 dimension. We really don't know what actually it is. But if we are calculating dimensions, typical vectors won't be able to do. So here comes another role of tensors, that is measuring dimensions. The next thing comes up is something which we call measuring stress energy momentum tensor. Now if I want to tell you what actually stress energy momentum, you can call it as a house where everything has got a safe place. What are those? This one, it is called an energy density, energy flux, and this mu nu denotes which space-time direction we are taking, which component of the form momentum is concerned, and this one is called the momentum density. This is the shear stress. So everything related to a matter's movement. When a matter moves, it will create an energy. There will be an energy density. There will be shear stress. There will be a strain. There will be a momentum. Everything has been encoded over here, even the pressure. So the role of tensor in general relativity is another one, which is called measuring the stress energy momentum tensor. That means whenever a matter is present, energy density, energy flux, shear stress, shear strain, pressure, momentum, and many other factors will be present, and in many dimensions, 3, 4 or maybe higher. How are we going to encounter and encode those information in the dimension? Stress energy momentum tensor is the answer. So I will expand a little bit. This is the matrix you see. This is the energy density. That means it is responsible for the space-time curvature. Pressure, if you squeeze something, it creates a pressure, also acts as a source of space-time curvature. Matter movement, it creates a kind of an energy flux which causes further curvature. Now you see, left one is the momentum density, which we call mass flow, multiplied by either momentum or mass. It actually shows the flow of momentum. All those taken together, energy plus momentum plus pressure plus stress, actually creates the curvature. And here is the curvature shown at the bottom of the screen. So the role of tensors is to measure the curvature. Otherwise, how will we find gravity? The next part is also, which is called, it measures the movement in space-time, which are called geodesics. Now geodesics, I don't want to expand further, are basically the shortest possible path that a particle takes. So if I take this kind of a line, I can generalize it into this kind of a illustration. So what path the timeline will take? This is the whatever the path it is laid down. That is, if it is curved, it will be curved. If it is straight, it will be straight, right? So generalizes the notion of straight line in a curved space-time, and this curvature actually causes the gravity. So the source, remember, is the stress energy momentum tensor. The source is the stress energy momentum tensor. The tram will take only the path which is laid in front of it. If it is a curved, it will create a curved space-time. If it is straight, it will be straight. And an object moves through space-time in straight line geodesics. But if it is curved, the line will follow the curvature. So this is another role of tensor, measuring the movement on space-time. It is not as easy as Newtonian mechanics that you get 2 points, but it is all on geodesics. So this is the effect which we call it as gravity. Now there is another thing which is called the role of tensors. This is this one, which is the movement when I move directly. It is called what is called a zero curvature. The size of the ball remains. This is called a positive curvature. You see, if I take a ball and it shrinks in size. So don't worry about this RIC. I will explain in later part of the video. This is called riccicurvature tensor, which is positive. Size of the ball shrinks. And here you see that the curve or the path is diverging. Here it is converging, so it is positive. Here it is straight, it is zero. But when it is diverging, what happens is the size of the ball increases. And that is why we called it as a negative curvature. I'm so sorry because right at the beginning of the screen, the negative and positive was there, but it should have come with the animation. But anyway, so this is called the negative curvature, positive curvature, and zero curvature. So the measurement of the curvature, typically I should have called it as a Gaussian curvature, but this curvature also is measured by tensor, and that is the role of relativity. Now here is a very interesting question. Most of us, whenever we talk to students, young people, they tell that it was Einstein who discovered, tensors. But the question is that, is it Einstein who really discovered tensors, or was Einstein not aware about tensors? A very interesting but a small quick history coming into this part of our video. This is a wonderful book which I would recommend you to read. Subtle is the Lord, written by Abraham Pais, very renowned author. Now I will take few lines why I am taking. I will just justify now. So here Einstein says, this problem remains insoluble to me until 1912, when I suddenly realized that Gauss's theory of surfaces holds the key for unlocking this mystery. And he writes, from him. Who is that him? I will soon reveal in a few seconds in this part of the video. I learned for the first time about the Ricci and later about Riemann. Einstein also says, whether my problem could be solved by Riemann's theory ... That means he stays confused. So in this book, I just cited 3 lines which shows that the inconsistency or the confusion or the complexities of the equation which created a doubt, and Einstein during that time when he was formulating the relativity was still not clear who will help him, how it will be solved, and which particular theory will lead him to the road of success. Here is this person I would like to talk, and Einstein was referring to this person, Marcel Grossman. Born on 9th April in Budapest, Hungary, he was the son of a large machine shop owner, and he was a descendant of an old Swiss family. He spent his childhood and attended school in Budapest, and at the age of 15, he returned to his parents in Switzerland. Now you see this famous picture, Grossman, Einstein, and Michel Besso. Now Einstein encountered another genuine friend called Michel Besso at the Swiss Federal Polytechnic School at Zurich, which is sometimes called an ETH, and it is here that they both of them wanted to explore the truth of universe. Now it was Grossman who helped actually Einstein with the geometry and the concept of tensor algebra. He needed to formalize the theory. He asked Grossman to search for the literature and look for existing appropriate geometry to tackle such questions. So if you are wondering that who was the person who helped Einstein, obviously Michel Besso was one of them, but particularly Marcel Grossman. The reason was that Grossman already knew tensor algebra, already knew Riemannian geometry, in one word, all about differential geometry. And in the next few seconds of the video, I will show you the original manuscript which shows that how Marcel Grossman helped Einstein. Okay, so this is I know this is a little bit hazy. I cannot help it. I downloaded from the Zurich Hebrew archive. So here you see that Marcel Grossman is introducing Einstein to the Riemann tensor as a mathematical resource for the general theory of relativity. So apparently Grossman had shown Einstein the relevant object that would open a path towards fully covariant gravitational field equation and to define Christoffel symbols. So here is another manuscript. Here you can see that this is what this partial derivation shows, the Riemann-Christoffel symbols. Now it is written here. So I have just expanded this so that you can see it clearly, because the handwriting of Marcel Grossman has faded out through history. So this one, which you can see right at the bottom, this is the page of the Riemann-Christoffel tensor fully written in covariant form. And this is what is important. You can see I've highlighted this in red. It is written as Grossman's tensor of fourth manifold. And this is an object that was needed, that at only two free indices, Grossman contracted the Riemann tensor and founded this wonderful equation. So this actually shows, to be honest, that Einstein was not aware at all about tensors and manifolds and differential geometry. And this writing shows the evidence how Grossman actually introduced tensors to Einstein, and how he calculated the Grossman tensor of the fourth manifold, and thereby helping him to form the theory of relativity. Now the question is that we have understood everything. We have understood the history. We have understood Grossman's contribution to relativity. Now we will understand finally what are the tensors that are used in general relativity, and a quick summary what actually the tensors mean. So first of all, the famous Einstein's field equation, I don't need to explain it further. So this first r mu nu, this is actually shows the dimensions in space-time. 0 is the time, 1 is the x-axis, 2 is the y-axis, and 3 is the z-axis. This g mu nu actually shows the dimensions in space-time. This is, it is a dimension in space-time 0, 1, 2, 3. Again, this g mu nu also is a dimension of space-time, which is 0, 1, 2, 3. This g mu nu again is a dimension of space-time 0, 1, 2, 3. Now you might be wondering why I'm constantly repeating the same thing. This is just to show you that these are actually, this mu nu shows the indices, that means which way you are using the space-time curvature, and this is what? 4 plus 4 plus 4 plus 4. 16 partial nonlinear differential equations frames the entire gamut, entire arena of Einstein's general relativity. So 4 for the first, 4 for the second, 4 for the third, and 4 for the fourth, all of them measuring the same thing, which actually makes it 16 equations. In my other videos, I would request you can go to my playlist. I have shown mathematically how the 16 equations are reduced to 10 partial differential equations, because 6 of them are common. Okay, now it is the time to subdue or fulfill or satiate our excitement. That is, what are those tensors all about? The first R is called the riccicurvature tensor. It actually measures how the volume of matter changes when it moves from flat space to curved space. Now, if you're wondering to know more, hold on. I will make another video, or rather I have other videos which actually gives you a very detailed understanding of what is a riccicurvature tensor. I'm making small shorts also to explain that, but now it is a time just to understand the basics. The second one, this R, this is called the Ricci scalar, or you can call it as a scalar curvature. It keeps track of how the size of a ball deviates from Euclidean space. That means if I move the ball in an Euclidean space, how much the deviation it will take place from the Euclidean space to a Riemannian space or a curved manifold. That is what Ricci scalar measures. The second one is called G, that is called the metric tensor. And what it does, it measure? It is a way of measuring all the causal structure of space-time. That is the angles, the lines, what the way it moves, everything. This is what G measures. Now there is another thing which is hidden, which is called the Riemann curvature tensor. This is too technical to explain right now, and it is actually describes the curvature of Riemannian manifold. Why it is hidden, I have explained in the other videos. It is actually contraction of the Riccian curvature and the curvature scalar. So that is why it is hidden. And then it comes to the final one, which is the T mu nu. It calls the stressenergymomentumtensor, and we have seen what it is. It is actually telling the matter movement through space-time. Now, taken everything together, can we finally find out a summary of this? Let us see in this part of the video. So this entire, okay, so this lambda, capital lambda, is the cosmological constant, c4 is the speed of light, 8 pi again comes from Poissor's equation, and g is the good old Newton's gravitational constant. So these are the constants. So the constants plus the variables actually measures or makes up the Einstein's field equation. So can we summarize it? Yes, we can. So the entire left hand side of the equation tells how to measure the curvature of space-time. That means it talks of the geometry of space-time. The right hand side, actually what it measures is called the matter energy content of space-time. That means if the matter is moving, how much energy it is creating, and obviously if it is creating an energy, it is creating a curvature, and it measures the matter movement. So if the right hand side is the matter which moves through the space-time and it generates a kind of a momentum, energy, density, etc., obviously that movement will create a curvature, and that curvature is being measured in the left hand side. That is the geometry of space-time. Together it is equated, and this is what we call space-time tells matter how to move, and matter space tells space-time how to curve. So that actually completes our entire video, and this is the time that we should summarize, because we have learned a lot. We have learned what is the definition of tensors. We have looked into the history of tensor. We have also looked into the role and importance of tensors, how tensors can be used in Newtonian mechanics to write in a clear and concise manner. We also have seen tensors, how it understands these crystal structures, what are the unique features of tensors, writing Newtonian equations, Einstein's discovery about tensors and its role in relativity, and how tensors play an important role in building the entire mathematics as well as the philosophy of general relativity. So I am immensely thankful for those who have watched my video. Thank you very much for watching this video. Please do subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID. You can further subscribe to my other channel, and you can follow me on my Instagram, Facebook, LinkedIn, and now on the Twitter account. What is new coming up is that I have already got a fan page which is working dedicated to the life and works of Stephen Hawking. You can follow. This is in Facebook, where I post mostly news and discoveries and inventions and researches related to science, physics, and sometimes interesting biography on a very lighter manner, not much of mathematics. So that's all for today's video. I hope you liked the entire story of the discovery, the invention, the role, the importance, and how Einstein, Bessel, and Grossman created the entire structure of relativity. What are the tensors and their role? Thank you very much. Do comment on this video and do let me know about how you like this video, and don't forget to subscribe, and thank you for watching. Physics for Students will be soon back with further more interesting videos. Till then, goodbye.